gotta take something as a compliment. Okay. Good morning. Thanks for coming to this talk. We're going to talk a little bit about the storage engine. Storage engine is not the query engine. We're going to distinguish storage engine from query engine. My name is Jacob Marble. I'm a software engineer on the storage team at InfluxData, and that is the storage engine in our 3 or 4 products. A little bit about myself. These are the people I care about most. I live in North Idaho, in the trees and the mountains and the water. InfluxData is a remote company, so if you are looking for a new opportunity, then discreetly reach out. All right, so let's build a time series storage engine. The storage engine is something that the query engine will reach into through an internal API. The storage engine is the bottom layer in this stack, and I like to think of, when I go to first principles, what's most important for my time at work is 3 things. We make sure that the data that you write arrives to disk safely. We make sure that the data that you read is complete and correct. And then third in priority is performance. We want those 2 operations, reading and writing, to be accurate first and performant second. So we'll build a time series storage engine 1 layer at a time now. Some requirements, some very simple basic requirements. We're going to have a write endpoint and a read endpoint. The write endpoint you might recognize. It's not very different from the actual write endpoint on InfluxDB. We take line protocol from a post body. And then the read endpoint is something that's a little bit contrived, but it does look very similar to our internal API. And we're just going to read line protocol back out of the database with that endpoint. So here's a clear specification for the write endpoint. If you're not aware, line protocol is the second line there. So line protocol is just text, and it's formatted for writing into the database. And the format is measurement, tags, field keys and values, and then time. And I'm just using whole seconds for the timestamp here. I'm not going to push out a bunch of zeros for nanoseconds to make this a little bit easier to read. And here's 4 example points that we could write to the write endpoint. All right, so let's implement the specification. Very simple implementation. The database itself is just an in-memory list, and we're going to siphon the post body right into the in-memory list. Basic, simple. So clear specification on the read endpoint now. I'm using an example to also describe the whole get endpoint here. So we'll be reading in this example, we'll read from measurement H2O feet, from the field keyed water level. We'll bound on time. So we have a start time, but in this case, no end time, so we're unbounded on the end time. And then a bunch of tags and keys, tag keys and values, in this case, location Santa Monica. So if we were to actually write these 4 points from the previous slide and then read them back with this query, then we should expect those 2 points to come back, okay? And here's the implementation of the read endpoint. Go back to the same global database list of strings, and any line that matches, return it. And there's our minimum viable product. So we wrap it up in a binary and ship it off to customers. They pay us lots of money, and they come back with some feature requests. They'd like the data to be durable. Written data should not disappear after the storage engine restarts. Seems like a reasonable request. We book some time on the calendar. Product agrees we should do this. So we implement we implement durability with this thing called the write-ahead log. Lots of databases use a write-ahead log. The write-ahead log is a data structure and algorithm that is super simple and super powerful. And buckle up, because I'm going to read this slide word for word. So when a client, you send a write request, we append that write request to the write-ahead log file, just append it to the bottom of the file, and then fsync the file. And then update the in-memory database, and then return success to the caller. Okay, fsync is the important part there. Fsync is a system call, so there's a kernel context switch in there that costs something. And what fsync does is takes the file and pushes any pending writes all the way through any buffers and caches to the actual spindles or chips. So fsync is kind of expensive, but it guarantees that the data is safe on disk. We could pull the plug and our Raspberry Pi wouldn't lose the data, wouldn't lose what we've written. This is why it's important to batch your writes, to send in a couple thousand points at a time if you can, so that we're fsyncing less frequently. Okay, now on the read side, when the storage engine restarts, we just open the write-ahead log file and read it back into the in-memory database. And after we've replayed, only then do we answer requests to the read endpoint. So we've modified the write endpoint a little bit here, added a wall file. We call it the wall. I'm just going to call it a wall because that's what we call it. In the write function, as soon as the write request is complete, we fsync the wall and then return. And then on startup, read it back into the database. Real simple, real powerful. And we codename this version 2 durability. And we spink it on the bottom, we send it down to the release engineers, and off it goes to our customers. Customers really appreciated that, but they would really appreciate it if they could store more data now. So the write-ahead log is great, it's durable, but if the storage engine terminates for whatever reason, we wanted it to or we didn't want it to, if the storage engine terminates because of out-of-memory problem, then it starts back up, the write-ahead log is read back into memory, we crash again with out-of-memory, and we never recover. Additionally, queries get slower as the data grows. We're going to tackle these two problems at the same time. So code slows as data grows. So to fix these two problems, we introduced the time-structured merge tree, which is similar to an LSM tree, a log-structured merge tree. Time-structured merge, so TSM is our data format. This is now real. TSM is our data format. Inside of TSM files, we group your data, which is to say we group field values by series key, and then we order the field values by time. Stuff that into a file that's called TSM. Okay, what's a series key? Series key is measurement name, your tags, so keys and values, and field key. We call that a series key. And then to wrap that in a broader concept, a point is a series key, and then a field value and a timestamp. So here's a bunch of line protocol for you to gaze at. Can you find the series keys? And I've put a reminder up there. Series key is measurement, tags, and field key. And here are the series keys. The measurement in all of this data is H2O feet. We have two tags, location Santa Monica and location Coyote Creek. And we have two fields, water level and level description. So in total, this entire data set, maybe it goes on for pages, I don't know, but this entire data set has 4 series keys. I recently learned that my manager has a PhD, so I use the word cardinality now. We have cardinality 4. Okay, here's the same data set, but this time displayed, I'm using the Influx CLI and an InfluxQL query to just select the same data, so it's formatted a little differently. Can you find the series keys in this data set? And of course, they're the same. Our measurement is H2O feet, tags, location, Santa Monica and Coyote Creek, and fields, level description, and water level. And I did cheat, going back here. I put an asterisk next to the tags excuse me, an asterisk next to the fields and then left location as the tag without an asterisk. It's a little bit ambiguous without that. Okay, so now let's dissect one of those series. So going back here, our first series key there is H2O feet, location Santa Monica, water level. So let's look at that series just by itself. This is a series. It's identified by the series key, and within the series you have timestamps and field values that are ordered by timestamp. Now, if you were to write code to handle this series, if you were to implement TSM, something you should notice right away is that a lot of data is metric data, a lot of data has regular intervals, and in this case the interval is 60 seconds. And another thing that you notice about time series data right away is that it tends not to vary wildly. So we have an opportunity here when we store this data to not only pack it in a columnar format, but also to compact it real nicely. So it is efficient to store this as on disk as series key, and then just 8 bytes for the timestamp and 8 bytes for the field value back and forth. That's pretty efficient. But a more efficient way, if we were to compact this data better, would be to store the initial timestamp, the interval, 60 seconds, the initial field value, 2.064, and then only store, maybe with 16 bits or 8 bits, depending on, only store differences between the field values as you go down that series, right? We use the word delta when we talk to our PhD friends. Deltas between these values. Here's the next series, very similar, regular intervals, not a ton of variation in the values. An even easier opportunity to compact here where in this particular series we just see the same value over and over again. So you can imagine compacting even better than the first two series and the fourth series. Okay, so once again, this is a series. So pivoting data this way, we call that column-oriented storage. Line protocol is more of a row-oriented storage. Reading only the series that a query needs is very useful, and TSM allows us to do that because now that the data is organized, is grouped by series key, an InfluxQL query can just get data from the series that it needs. We don't have to iterate over our entire data set. So queries are fast, and then of course compression or compaction is very efficient and also helps with performance. And one small detail here is that now that we've implemented TSM, that in-memory database, that list of strings, is not invalid. We have not thrown that away. We still use it. The way this works is we get a write from the user, we write it to the write-ahead log, we store it in the in-memory cache, and then after we've collected about 10 minutes or 25 megabytes of data in that cache in the write-ahead log, then we do what's called a snapshot operation. We take that in-memory cache and put it into a TSM file, and then truncate the write-ahead log and clear the data from the cache. So that's configurable in the InfluxDB config files, but it's a small detail. We have not gotten rid of that cache. So we've got a little bit of scale here now. We can grow our data way beyond the size of memory on the system. In fact, we can store more data on disk than the size of the disk because compaction there's lots of opportunities for good, efficient compaction in time series data. So customers love the new product. They come back with another request. Queries are getting slower as cardinality grows. So we've solved the problem of queries getting slower as data grows, but now queries are getting slower only when cardinality is high. Why does that happen? So here's an example. We want to select everything from H2O feet. Well, that means that we need to find the series keys that belong to H2O feet, right? The H2O feet measurement. To do that, we have to iterate over all the series keys and find matching series keys. So if we only have 4 series keys, that's real easy. But if we have a million series keys, it's a linear operation. It's going to take forever to find. Every query has to search through every series key to find the ones that are relevant to that particular query. So this is where the TSI index comes in. TSI is like TSM. Let's go back and review what TSM is. TSM stores data, which is to say it stores field values grouped by series key. TSI stores series keys grouped by measurement, tag, and field. It's a data structure, it's an algorithm, it's an on-disk format. So TSI is good at answering these 2 questions. What measurements, tags, and fields exist? You ask that question whenever you issue a meta query, like show measurements or show tag key values. And then the other question it's very good at answering is, given a measurement, some tags and fields, which series keys exist? So with fast series key lookup, cardinality capacity is much higher. And so once again, we can scale our data a little bit more. So TSM and TSI are married. Sometimes people mistakenly ask the question, well, should I use TSM or TSI? That's not a valid question. TSM is how we store data. TSI is the index that we use to reference the data. All right, next feature request. We've got an enterprise customer. They would like to scale further. And we notice in bigger customers, we notice that in bigger data sets, most of the queries are on recent data, and very rarely do we see queries on historical data. Can we optimize this somehow? So we'd like to partition the read and write load over time and over storage engines. And we do that with shards. So I've described the write-ahead log, told you about TSM files that store data and TSI files that are indexes. A shard is just a stack, a package, a bundle of those 3 tools. And a shard is a file system directory that contains all of those things. Shards are time-bounded, so a shard has a begin time and an end time. When you're right into a shard and the clock is ticking, eventually that shard's end time will come and we'll open up a new shard and you'll start writing to the next one. So we'll zoom out a little bit here. In InfluxDB, an instance of InfluxDB has 1 or more databases. Each database has 1 or more retention policy, and then a retention policy typically has many shards. Properties of a retention policy are duration and shard duration. So the retention policy duration says that after so much time, I'd like my data to go ahead and quietly be deleted. A unique property of time series databases. Most relational databases, we don't do that. And then shard duration is, how do we chunk up the data? How do we partition that data within the retention policy? So if you have a retention policy of 30 days and a shard duration of 1 day, we should expect there to be roughly 30 shards. Okay, and then the retention policy is responsible for creating a new shard whenever data is written outside of the boundaries of the current shard set, and so shards have start and end times as properties. So an example here of, or an illustration of shards as segments of time. In this example, retention policy is called daily. Not a very good retention policy name because it's actually hourly, but no, this is daily. Yeah, this is fine, okay. The retention policy is called daily, so it has a duration of 24 hours. So we expect data to delete quietly, implicitly, without an error after 24 hours. Shard duration is 1 hour, so we have roughly 24 shards. The current time is May 28th, 4:15. And so shard 29 is what we call the hot shard, because the current time falls within that window. So shard 29 is getting a lot of, I mentioned before, snapshotting. Shard 29 is being snapshotted constantly. We're not going to do a lot of like full compactions. We aren't doing a lot of super efficient compactions. We're mostly just getting the data onto disk. And then shards 28, 27, 26 are starting to go cold, so we're doing more efficient compactions, what we call full compactions, to get that data as small and compact as possible on disk. And then shard 4 is about to go away because shard 4 time range is more than 24 hours ago. So we should expect shard 4 to disappear soon and not tell us anything. So this way of doing things with shards is helpful for implementing retention policies because we simply delete the directory. When a shard has expired, we just delete the directory. It's not quite that simple, but it's almost that simple. Okay, so shards also allow us to do horizontal scale. When we've divided our data into shards, it's easier to talk about replicating shards and spreading the load around multiple storage engines. And this is how InfluxDB Enterprise works. By doing that, we have more capacity for storage and more capacity for query load as well. So version 5 is shipped. We call it sharding, and this is kind of the complete package of the InfluxDB 1.7 storage engine. So what changes in 2.0? The write-ahead log in Cloud 2.0 is now in Kafka. Apache Kafka has, well, in case you don't know, Kafka is like a publish-subscribe type of a tool. It scales very well. We don't use it like most people use it. We don't use consumer groups. We actually push directly into Kafka topic partitions. So partition 0 corresponds with shard 0 in the cloud environment, and partition 1 in Kafka corresponds to shard 1 in InfluxDB. We found Kafka to be very reliable, and nothing more to say about that. In TSI, so in 1.7, I actually lied a little bit before. We don't store field keys in TSI, but in 2.0 we will. We do. And then the shard paradigm changes a lot in 2.0. So in the open source InfluxDB, we just have one shard. We have one write-ahead log, one set of TSM files, and one TSI index. And then in 2.0, we have shards, but they're just for horizontal scale. We do this because some customers, well, we've got a couple of features that have been requested for a while. One of those is cold storage. Some customers want to store data forever. Like they literally want to put in 20 years of historical data and reference it forever. They don't want it to be cleaned up over time. In order to do that, we needed to do some refactoring because you can't have, if we support infinite time, then that means we support infinite shards, and that just isn't feasible because it's a lot of indexes to reference and queries that go over a wide period of time become very expensive. That pretty much sums up why. So some of the implications of this new shard paradigm: retention policies can no longer be implemented as just delete a directory. Instead, we had to get smarter about bulk deleting data out of TSM files. So there's an internal function we wrote called delete with predicate. So now we can tombstone like whole batches of data with a single tombstone rather than deleting data kind of one series at a time. So bulk deletes are more efficient now. Queries that read over large time periods just hit the one shard rather than hitting all the shards. And then the blocks inside of our TSM files are time-bounded now, and that makes it easier to only reference the TSM files that we need, so that becomes less of a problem. So in summary, write-ahead log is an amazing, simple data structure. There's a Wikipedia page, you should go read it. TSM is our data format. It's where we store field values grouped by series key, ordered by time. TSI is our index. TSI stores series keys grouped by measurement, tag, and field. And then a shard is this stack, write-ahead log, TSM, and TSI. And then in 2.0, I've only talked about maybe half of the things that are really changing in 2.0. We're still in the design phase and decision-making on some of the other changes that will be coming, but I hope that some of this is clearer. And of course, the end goal is a better product and better performance and all those kinds of things. So thanks for your attention, and what time is it? So I've got time, wow, for a lot of questions. Yes, go ahead in the front. So the question was, after you write some data, and you want to know how much data was written to disk?
Yeah, if, for example, I want to immediately shut down InfluxDB,
yeah.
I want to guarantee that my data was actually stored on the disk. So how long
okay.
do I get a notification? Can I get a notification?
Yeah. So if you've written data to InfluxDB and the write endpoint has returned success, then it's safe on disk, and you can shut down immediately. That's the magic of the write-ahead log, and we call that durability. We don't guarantee that it's readable immediately. In the open source InfluxDB, it happens to be that it is readable immediately, but in enterprise, it's eventual consistency, and so it's readable within a tenth of a second or less. But it is, if our API returns success, then your data is on disk.
Is there a possibility to configure the amount of a shard length when you're
Yep.
building?
It's if you're in the Influx CLI, it's create retention policy, something with shard duration 1 hour. So go to the docs for create retention policy, and that'll tell you, and you can also modify shard duration. Yeah.
Still the client's responsibility to sort tags so that you don't create multiple series for what is the same set of tags?
Is it the client's responsibility to sort tags when you're writing a batch? It's not, but on our side, we will sort the tags. So if you're pushing up against some write performance issues, then you could sort for us and then write the batch. But no, there's no, for correctness and durability reasons, there's no reason to sort the tags before you send it in. Yes?
In 2.0 OSS, if there's only a single shard, how does disk space reclaim work?
How does disk space what?
Reclaim work. If I can simply delete a directory with the shards that are out of my window, how does the engine reclaim the disk space?
Oh yeah, so this is kind of fun. So in the write-ahead log, we have two kinds of entries. One is write some data, and the other is delete some data. And we call that one a tombstone. And so we write the tombstone to the write-ahead log. That tombstone is recorded in TSM, and we check it. So we look for tombstones on every query. So every query we go back and say, every read request, we go back and say, okay, here's the series that the user wanted. Now let's check the tombstones to see what we need to filter from this response, and then return to the user. And then in a compaction event, so some point in time later, we will rewrite those TSM files to make them more efficient and also to remove tombstoned data. So the illusion to the user is the data was deleted just like that, and the reality is it takes something between 5 minutes and 6 hours for that compaction event to eventually occur and actually delete the data from disk. Yeah. Sir?
So when horizontally scaling InfluxDB on like multiple nodes, how does shard assignment work on like different nodes, for example? guess.
How does shard assignment work on a horizontally scaled InfluxDB instance? There's a lot of literature on this. It's basically a replication and then spreading it around evenly. So for example, if you wanted full replication, then that means that every storage engine would get a copy of every shard. That's one way to do it. Another way, otherwise we just try to, there are various algorithms to decide like where a shard should go within a cluster, and that's a whole other hour-long discussion. But you can Google that as well, or ask me later if we aren't being clear with each other. Yes, sir.
About field types, you have the different types on different or on the same field. You can in Influx have different series with different types on the same field. Where does field type fit into your description?
Yep. Yeah, I definitely glossed some icing over that part of it. So field type, InfluxDB is a schema-less database. So we create the schema and you write the data. Field type is stored in the series key, and so we should be able to catch that and tell you that you can't store data of a different type in a field that already exists. There was a bug. There was a bug in the last 6 months we worked on with this, and it had something to do with field type, and I wish I could. So I think in 1.7 we stored the field type only in TSM, and now we store it also in TSI as part of the series key. Yes, sir, in the front. Backup and restore. Yeah, that's totally out of band to all of this, and I don't have a simple answer for you on stage. Yeah, maybe we catch up afterwards. Yeah. Okay.
When we were experimenting with InfluxDB, we realized whenever we were trying to insert some numbers, by default, it was storing it as a long. And for some bigger number, it was rounding up. So on the community, people pointed out to mark them as an integer. So now all our numbers carries the postfix of I to make it as an integer.
Yes.
And I realized whenever we dump the first row in any of the records, which is the first member of the series, at that time you guys define which is the data type of which field, that thing. And after inserting the long, if I'm trying to insert the integer, it will throw the error. And means this thing is happening. And so now eventually all of our numbers are postfixed by the integer. So is there any straightforward way to define which field is an integer and which field is a long, so all the numbers won't carry the integer I, postfixed I, simply? Because with a very huge data, it is increasing the size of the packet which we are trying to impose.
Yeah. So you've stored some data as longs, and now you want to store them as integers. Is that right?
Yes, we want to store as an integer.
Yeah.
But defining that I, one extra character.
Yeah.
And if I am ingesting the very huge data, it is
Yeah.
eventually increasing the size of
Yeah.
the data packet. And I believe the only first entry matters. So
That's correct. Yeah. So when you write okay, so let's go back. So you've written some data as long in a field with the type long, and now you want to go back and change that to type integer, so that because of the suffix in the line protocol. Okay, so we want to change the type. Changing data type is not easy. The easiest way to do it is to just create a new field, and then start writing into that new field. Maybe write your queries to consider both, move it over, something like that. But we could talk about operational steps to mitigate that, maybe in the room 2 over after this. Yeah. In the front here, yeah.
Yeah, I think you might have just answered my question, but if I write a bunch of points with, say, 5 or 6 fields, and then one of those fields I decide I no longer want to write, will subsequent shards then no longer, or subsequent series in shards, I guess, no longer carry those extra fields along if they don't exist in the in all of the writes in that.
That's right, yeah. So think of a shard as a very small database. The question was, if you write some data, you create some series in a particular shard, and then stop using some of those fields later, do subsequent shards carry like the field but empty? And the answer is no. Every shard is created basically from whole cloth. And so we recreate, and that's a change in 2.0 is we don't, if your retention policy says the shard duration is 1 hour, you're creating a new shard every hour. That means that you're probably creating an identical TSI index every hour. And so in 2.0, we're changing that so that there is only one TSI index, so they're not recreating it all the time. In that case, compaction will eventually delete the fields that you're worried. Like once the data is gone, then the series key is gone as well. In the middle there.
Yeah, so are there plans to have derived data types to store like arrays in fields?
Derived data types?
Yeah, like arrays in fields.
I don't think so.
Yeah.
Right now I would do that either with multiple fields or with a string that's just comma delimited.
All right. Okay.
But it's, yeah, I don't see that on any of our like future plans.
Okay. Great.
Okay.
Could you elaborate how the sharding works in your cloud edition? Specifically, I'm interested. So let's say we have multiple tenants, right? And do you mix time series from different tenants within one shard?
In Cloud 2.0, it's a multi-tenant architecture, yes. That's necessary to make the pricing and scaling more elastic with our customers. In Influx Cloud 1.7, you buy an enterprise cluster and we manage it for you. So it's totally isolated in that case. And in 2.0, we'll have the option to do like private clusters. But yeah, that's a fun problem too, is to manage multi-tenant data and get it right. Over here on the left, my left. Go ahead.
Check. If you could please wait for the microphone for the recording. Thank you.
Cool. Is it easy to switch the storage backend for the TSM and TSI? Like, let's say I want to store an S3 or other object storage.
In Cloud 2.0, we'll be able to store cold data in an object store like S3. But in 1.7, we don't do that yet. So no, it's not easy, and that's why we haven't done it.
So how does switching to Kafka as your write-ahead log affect the binary distribution model that 1.x was using?
Let's see, I heard most of that. Can you say it again?
Sorry, how does switching to Apache Kafka affect the binary distribution model that you were using for 1.x?
The binary distribution model.
Right, yeah, so you were able to just download this one binary and run the database and install it, but now are you going to have to basically install all of these extra dependencies to get Kafka running?
I got this question last time I gave this talk too. In OSS, in the open source InfluxDB, Kafka is not required. It's not necessary. It's not even available. You could use Telegraph if you need that. You could use Telegraph to write into Kafka, then read out of Kafka and push into the database, if that helps you. In Cloud 2.0, we've decided to go with Kafka because it scales very, very well. So we can handle many tenants of many sizes. That's all. Okay.
So I was curious how these TSM files compare to, say, so a Parquet file that that the Hadoop infrastructure uses. They sound superficially similar. I'm just curious if you can draw a little deeper.
You're right. They are superficially similar. Yes. Parquet is definitely a columnar file format. It's general purpose. TSM is like laser focused on time series data. If your data doesn't have a timestamp, it won't fit into TSM. So it's more efficient than Parquet for time series data, and I wouldn't be putting like GIFs into time series database, if that makes sense.
About how long until an on-premise version of Influx 2.0 is available?
You have to talk to our product people, but not right away. Yeah, we're committed to keeping InfluxDB Enterprise going for a while, especially because those customers tend to be the ones that are the most hesitant to upgrade. And we want to make sure we get that right for them. And also because a lot of customers really want the managed service that Cloud 2 is going to provide in a smaller, more affordable scale and an elastic scale where they pay for usage. So that's the more compelling, I think, business, but I'm not on the business side. So. Okay, well, thank you so much for your attention, and have a great day.